Okay, Gage. I think we should get going soon, right?
Right. So we are actually being recorded now. So
I pressed record. Yeah, you can see that.
So let's pass it over to Kira. Huh?
Yeah. So just a couple of housekeeping things. Please, if you're not the speaker, please mute yourself so everyone can hear the speaker clearly. And if you have any questions, if you're watching in the Google Meet, just type them in the chat and we will get you to ask them probably at the end unless they're super pressing. If you're watching on the YouTube live stream, you can also ask your questions by typing in the chat there and we'll ask any relevant ones at the end. The seminar will be about 50 minutes and then 10 minutes for questions afterwards. And I think that's most of the admin things. Anything I'm missing? Do you know?
No, I think so.
Okay, so I'll hand you over to Gergo to introduce the speaker.
All right, welcome everybody. It's my great pleasure to introduce our second speaker in this wonderful seminar series, who is Matthieu Geist. So Matthieu did his PhD with under the supervision of Olivier Pietquin at the University of Metz. And then he became an assistant professor at Supélec, later called the Central Supélec, also in Metz. And later he joined the University of Lorraine as a full professor. And lately he's been a research scientist at Google Brain in Paris, commuting between Metz and Paris. So you may know Matthieu's fantastic works on reinforcement learning theory. He did reinforcement learning theory before it was cool. He made like a bunch of contributions to approximate dynamic programming, approximate policy iteration, and all sorts of fundamental results of reinforcement learning theory. And lately he's becoming interested in a very trendy topic, which is regularization and reinforcement learning. And he's going to be telling us about that today. So please welcome Matthieu.
Thank you, Gage. So I present our last work on reinforcement learning, on regularization in reinforcement learning. And this is a joint work with Nino, who is doing a PhD at Google, Olivier Pietquin, Bruno Scherrer from INRIA, Rémi Munos from DeepMind, and Tadashi Kozuno from OIST. And as a warm-up, I will start from deep reinforcement learning because that's what people look at currently, to go back to dynamic programming. So if you take just the update rule of DQN, this is what you optimize with gradient descent. You have a target policy, which is the policy being greedy according to the target Q network. And you evaluate this the target Q network in this policy. And so you have a greedy policy, and you update your function towards this target. And so you apply a sampled version of the Bellman operator, and you do some error that comes from sampling, that come from the function approximation by the neural network, and so on. So if you abstract this a bit, this is approximate value iteration. We have two steps. The first step is the greedy step. You compute the policy, which is greedy according to the Q function. And the second step is the evaluation step. You just apply once time the Bellman evaluation operator for the greedy policy to the Q function, plus some noise that comes from sampling, function approximation, and so on. And this is the scheme that I will modify to take regularization into account. So the question is, so DQN is basically approximate value iteration up to many smart things that make it work. But if you look at dynamic programming, it's approximate value iteration. And is this algorithm good? And the response is not that much. Because if you take a very simple case, you have a tabular representation, that is, you have a finite state and action space, and you can represent the Q function exactly. You have a generative model that you can call for any state action pair. You can call for a sampled net state. And in this case, The only error comes from sampling, and the errors are a martingale difference with respect to the nature of filtration. You can think about errors that are zero mean, bounded, and roughly independent. And in this case, if you look at the bound of approximate value iteration, it's so you have an error which is zero mean, but the scheme doesn't converge because the bound will depend on 1 over 1 minus gamma, the origin, and it will depend on the sum of the norm of the error. So you cannot have compensation of errors between iteration, and you have this kind of behavior empirically. This is the orange curve is value iteration. But if you have zero mean error, what you have to have is something that converges like the blue curve. So the question is, how can we manage to have the blue curve just by sampling one transition for each state action pair, which is not possible with value iteration. And we'll see that adding regularization allows achieving this. So I'll introduce some notation that will be useful later. So basically, I will write everything with dot product. So the dot product between pi and q is the sum of reaction of the policy in this action and the q value for this action for any state, and the pi dot q is a component-wise dot product indeed, because it's homogeneous to a value function. It's a vector in R over S. P times V, P is a transition kernel. It's basically the expectation of the value over the next state. So if you use this notation, you can write P pi Q as R plus gamma times the transition kernel times pi dot Q. Pi dot Q is the value function. The greedy policy, it will be the policy that maximizes pi dot Q over the simplex. So you might have more than one solution. And the entropy and KL divergence that I will use a lot can be written like this. So this is the classic entropy, my minus pi dot log pi, and you have the Kullback-Leibler divergence. And with this notation, you have approximate value iteration. So you look for the greedy policy, and then you apply the Bellman operator. And you see that what you optimize in the first step and what you apply in the second step are similar. So I will not talk about regularization. And first, I will start with regularization in the greedy step. This is the classic entropy. Sorry? I thought there was a question.
I think there was just some echo.
OK. So I talk about regularization, and first regularization in the greedy step, which is what people do usually. So if you have no regularization, so in all the scheme, I will show the triangle is indeed the simplex, and the initial policy will always be the uniform policy. So you're in the middle of the simplex. Here you have three actions. And the classical greedy step is just you take the greedy policy. So assume that the Q value are different for each action. So the solution is unique. So you will have pi 1 will be in a corner of the simplex, and then pi 2 will be in a maybe different corner, and so on. So when you do value iteration, you necessarily be in the corner of the simplex. Now, if you add some entropy, the entropy is a penalty that says try to compute the greedy policy while not being too far from the uniform policy. So you will start from pi 0. You will compute pi 1. So the red dot is the pure greedy policy, and the pi 1 is something between the initial policy and the red dot. And you will be necessarily inside the simplex. And pi 2 will be something like this. Next, instead of saying, I don't want to be too far from the uniform policy, you can say, I don't want to be too far from the previous policy. So in this case, you have a pi 0 as before. Pi 1, it will be the same thing. because pi0 was a uniform policy. But for pi2, you will have something which will be between the pure greedy policy and the previous one. And you can also mix both. Say, I don't want to move too far from the previous policy and from the uniform policy. And in this case, you will ask pi2 to be a kind of compromise between pi1 and the uniform policy. You can do other things. For example, you can regularize through the Q values. So the idea is, instead of being greedy according to the last Q function, you will be greedy respectively to the sum of all past Q functions. So you will still compute deterministic policies, but this makes sense. So to get an insight on why it makes sense, here's the rationale. Assume that Qk is the Q star plus some error, and the error is independent, zero mean, and bounded. So this is not what happens in practice, but just to explain the idea. If you consider classical greediness, it will not converge because you will be greedy according to the correct quantity plus some noise that change at each iteration. But if you sum this, the errors will cancel, and asymptotically we'll have a stable policy that will converge to pi star. So this is another way of doing regularization through the Q values. No.
So maybe I can ask a quick question here.
Yes.
So would you think that this is related to the idea of fictitious play in game theory, where you're trying to like find an optimal policy for the average of all the payoffs from the past? No.
So this is something I'm trying to figure out currently. It's a bit more complicated, I think, in game theory, because you have additional things that apply. First, right. It's not a distribution; it's really the sum of Q values, and you have only one player. So here, really, the aim is to cancel the noise. And in fictitious play, it's not to cancel the noise, because even if you know perfectly the problem, if you know perfectly if you take a simple matrix game, a zero-sum matrix game, and you have the matrix, you can compute the best response exactly, and so on. It will be unstable. But I think they are stunning, but that's not that clear.
Mm-hmm. Yeah, I see. Yeah, I guess we can talk about this later. Yeah. Sorry about the interruption.
No problem. So we have talked about regularization in the greediness, but we can also talk about the evaluation step. And this is something that is sometimes ignored in the literature. So the naive approach is just that you have a general greediness. You put some regularization. It can be the Kullback-Leibler divergence, the negative entropy, or say something else, whatever. And you can just consider the usual evaluation step. So this is quite classic in the literature, and this is called type 2 in my own nomenclature. I'm not good at finding names. But a more principled approach, at least from a theoretical viewpoint, is to also consider regularization in the evaluation step. So it makes sense because you have a similarity between what you optimize there and what you apply your transition kernel. So it can be practically easily done. It just amounts to modifying a bit your Bellman equation. It's much usual in the literature, so it's not that unusual if you consider an entropy regularization, but it's much more unusual when you consider a Kullback-Leibler divergence. I will talk about all-related approach a bit later. And this is called type 1. So as a summary, this is what I called, sorry, mirror descent value iteration. So mirror descent is because the greedy step is somehow reminiscent of mirror descent in convex optimization or in online learning. And so type 1, you consider regularization in the evaluation step, and type 2, you don't consider the regularization in the evaluation step, and the greedy step is the same for both. So there are many ways to do regularization, in the sense that you can consider type 1 or type 2, you can consider solely entropy, solely Kullback-Leibler divergence, or you can consider both. So this makes a lot of variations. And the thing is that all these approaches are quite related. So I'll start with just the entropy on type 2. So this is this scheme. You have the entropy in the greediness, but not in the evaluation. And one can show that it's equivalent to applying the Softmax Bellman operator. So this operator appears in a few papers. And basically, instead of, it's kind of the Bellman optimality operator, but instead of doing the max over Q value, you compute the softmax according to current Q value, and you compute this. And if the temperature here goes to 0, you retrieve the classic Bellman optimality operator. The problem is that it is known that even if you don't have error, this might not be convergent, because this operator is not necessarily a contraction, contrary to the usual Bellman operator, and it can admit multiple fixed points. And this means that regularizing the evaluation steps is important, because everything is fine if you add the regularization in the evaluation step. And if you look at the Melomax policy, so it's a paper from Assar, I think, and Littman, they introduce a quite complicated way to correct the softmax Bellman operator, which in the end is just adding some regularization in the evaluation step. So now we can consider the type 1. I just add the entropy to the evaluation step, and soft actor critique and soft Q-learning can be derived from this dynamic programming scheme. Up to some additional stuff if you consider continuous actions and so on. But the abstract DP scheme is this one. So we can analyze the propagation of error of the scheme, and if you compare to, in the left you have classic value iteration, and in the right you have the propagation of error for this DP scheme, and the sole difference is that you don't bound the same quantity. You can show that there's this scheme without error will be convergent. There's a unique optimal Q function. There's a unique optimal policy, and the policy is unique thanks to the regularization. And but so you by adding the entropy term, you put some bias on the solution, and you will converge to this biased solution without error. And with error, you will have the same propagation of error. That is, this is basically just like value iteration, but it converges to something different. So this doesn't explain why putting entropy is good, but this is only part of the story, in the sense that there are other works who advocate that using entropy regularization can help for exploration or robustness, or that it will smooth the optimization landscape, which is quite important when you want to do machine learning.
Sorry, Matthieu, can I have a quick question on this bound? Yeah. So the right-hand side of your bound does not depend on this temperature parameter tau at all, right? It's only the left-hand side. So, yeah. But maybe there's a hope that for, say, higher temperatures, the epsilons can be controlled more nicely, or the maximal V can be controlled more nicely, that it helps somehow the estimation errors?
If you put a very high temperature, the optimal policy would be close to be uniform. Mm-hmm. So typically, if you start from the uniform policy, you will find it quickly because it's a uniform policy. But right, from the propagation, so practically speaking, but maybe you can try to get some adversarial initialization, and it won't work as well. But you're right. Basically, if your temperature is high, your value function will be very high, very some constant, and you will be good. But
very easy to estimate. Yeah, sorry, epsilons are going to be small.
But they don't experience the right hand side of the bond.
So then this seems to suggest that maybe comparing these upper bounds doesn't tell the full story.
Yeah, that's what I was saying. But empirically, there are evidences that adding some entropy will help, clearly. But this bound tells nothing. It's just about how the error will propagate in the optimization scheme. So this assumes that you can compute the greedy step exactly because there's no error there. And it tells nothing about exploration. It tells nothing about how it's hard to solve this optimization problem. So you can have an analytical solution if you have discrete actions, but not with continuous actions, and so on and so on. So it's not a full story.
That's good, thanks.
So now I'll go back to, I'll go next to adding a Kullback-Leibler divergence and type 1 first. And dynamic policy programming can be derived from this DP scheme. So how this algorithm is justified indeed, because it's a bit different. And the core thing is that you have this you have this equivalence, because basically, if you look at this greedy step, you can compute the solution of this analytically, and the policy pi k plus 1 will be proportional to pi k times exponential qk over lambda. And by a direct induction argument, you can show that it's proportional to it's somehow softmax with respect to the sum of the previous Q function. So this is basically doing the regularization of Q values I was speaking about before. So this is a scheme you have. H is the average of the past Q values, the true average. Pi k plus 1 is greedy according to H, plus an entropic term that will vanish asymptotically. And you keep the same evaluation step. So this is the true equivalence. And through this equivalence, you can show that this scheme generalizes PDQ learning. PDQ learning that was introduced as a reinforcement learning algorithm with a good sample complexity, but without reference to entropy, to Kullback-Leibler divergence.
May I have a quick question? So it seems that you're tying the regularization coefficient in the two updates. Is there a reason to do that? Like,
It's just to have the equivalence between both schemes. It's for having the. What do you mean by tying the regularization?
you use the same regularization coefficient lambda, at least on this slide, in these updates. Why not use different? Like, is there a principled reason to choose the exact same value of lambda in both updates, the pi update and the q update?
Yeah. Okay. You mean in the evaluation step, in the greedy step, and in the evaluation step, we could consider different lambda, right?
Yeah.
I've never tried it. If you take lambda and 0, I will talk about it just after. If you take lambda and lambda prime, I've not. I don't know. We didn't write it.
That's fair. You have to start something.
So there's a reason for considering the same lambda is that you can consider the reward function. You can augment this reward function with a policy-dependent term. Will be, for example, you replace the reward function by R plus tau time the entropy of the policy for this given state. And if you do so, you end up with this DP scheme.
Okay,
it's another equivalence.
Yeah, some nice things are happening if you tie the two lambda or the two regularization coefficients.
And then you have a Bellman operator, which is contractive, and so on and so on. And if you don't tie them, I'm not sure of what's happening.
Yeah, there was a comment in the chat about proximal updates, and the question was like, is this similar to some proximal updates that people proposing gradient flows? I guess it is.
There are links to mirror descent, to follow the regularized leader, and this kind of thing. But the proof, so I won't show the proof just about, but the proof are quite different from what you would do to prove things with FTRL or mirror descent.
All right.
Yeah, so I also have a question along these lines. So like on the surface, this result really looks like the classical equivalence between mirror descent and the FTRL on the simplex. But
Absolutely.
I guess, but my question is, does this result also apply for policy iteration rather than value iteration, in which you fully evaluate the policy in the policy evaluation step?
So no.
Okay, right, cool.
So, okay. This is ready for value iteration, and we have the proof for value iteration. If you consider policy iteration or mirror descent policy iteration, or modified policy iteration, you can show that this kind of scheme will not break, and that you will converge if you have no error to the optimal policy, and you can show kind of propagation of error, which is similar to the one you have in classical programming. But there's something that breaks if you don't consider value iteration, because it's somehow so it's not only the aligning between the coefficient, but also between what you do in the greedy step and the evaluation step. And if you put a power m here, it won't work. At least it won't work for the nice bound I will show. It will work if you don't care about having a nice bound. But for the nice bound I will show, I was not able so far to extend it beyond the value iteration. And I think there are some structural problems to do so.
Yeah, but I guess it's not only the bound, but rather the equivalence between these two rules, right? That is the one that
the equivalence to will break. But all the bounds that I will show are based on this scheme.
Okay.
And they work for this scheme. But if you and then they apply to this scheme because they are equivalent. But what is analyzed is really this scheme. But you can imagine to do a scheme like that, which is more like PI, but even so, so you will somehow lose equivalence, but it's not even sure that it works well. I mean, from a theoretical viewpoint, because some of the approach I will talk about are indeed a PI scheme.
Okay, very nice. I'll let you talk about it then.
So this is, on the left, you still have the bound of approximate value iteration. And you have a square dependency to the horizon, because you should weight the sum by 1 minus gamma to have something which is a normalization factor. So you have a square dependency to the horizon, and here you have only a linear dependency to the horizon. This is rather nice because very few reinforcement learning algorithms are only a linear dependency to the horizon, and it's even known that for value iteration and policy iteration, the square dependency to the horizon is tight. And another core difference is if you look at the error term, here you have the sum of the norm of the error, and here you have the norm of the average of the error. And this means that you can have a compensation of the error. And in the ideal case, as I talked about before, where your error are roughly independent on zero mean, it means that this term vanishes asymptotically and that the algorithm will converge. So I recall the figure I shown before. In blue, what you have is this scheme for a given value of lambda. And it converges to the optimal policy contrary to value iteration. And I think this is a very, this is one of the, this is a nice thing about using a Kullback-Leibler divergence in reinforcement learning, at least from this analysis.
And could you get the same effect just by averaging the Q functions and just doing the regular value iteration analysis without regularization?
So, it's somewhere in the next slide.
Okay.
You can
sorry about all these questions.
you can, if you do so, you have a bound that show a compensation, but not so nice. And the last thing is, the last term is the convergence rate, in the sense that it will be the convergence rate in the absence of, without errors. And here you have a gamma power k, and here you have 1 over k. So if you don't do error, the convergence is slower, but it's where you are, when you have errors, that the bound is beneficial. And if you consider Kullback-Leibler divergence type 2, you have you just remove the Kullback-Leibler divergence on the evaluation step, and TRPO and even more MPO, so trust region policy optimization and maximum and posterior policy optimization, are close to this scheme. But these two algorithms are indeed, so it's less true for MPO, but TRPO is in principle policy iteration algorithm. So you have algorithms that are more PI-like and that works well empirically. It also generalizes momentum value iteration. So momentum value iteration is like value iteration, but so you just do value iteration, but instead of being greedy according to the last policy, the last Q function, you're greedy according to the sum of all past Q functions. So that's what you suggested, Gagay. And the thing is that you ignore, if you do so, you ignore the evaluation, the regularization and the evaluation step, and it changes a bit the result. It can also be seen as a value iteration-based variation of polytext that is an algorithm which is motivated from follow the regularized leader, or prediction with expert advice that Chaba know well. And so it's basically it's like momentum value iteration, but in a policy iteration scheme. And the analysis is done for the average reward case. There are some difference, but on a high level viewpoint, they are close. And if you look at the analysis on the right, so you have this error term, which is the same as before. And here, the big epsilon term, it's the sum of errors. So you still have a compensation, but these errors are preconditioned by the transition kernels of matrices of policies that depends on this error. So it's somewhat nicer because in addition to the temporal averaging, you add an iteration averaging. You add an averaging over the state space. So you average even more. It's good. So it should reduce the variance of this error and not change its mean. But this would be true if you were doing this averaging through arbitrary kernels, transition kernels. And it's not the case. Indeed, these kernels depends on the error term. And so it's hard to tell what's happening exactly. But empirically, it works pretty well. And next, what you can do is you can mix entropy and Kullback-Leibler divergence. And you obtain this scheme. And an algorithm called conservative value iteration by Tadashi, who is also co-author of his work, can be derived from this scheme. And thus, advantage learning, the thing that will add a kind of action gap to your Q function, can be also derived from this scheme, as it's a special case of CVI. So if you write the equation, it amounts to replacing the reward by the reward plus the Q value minus the maximum Q value. It also generalizes momentum DQN, which is a deep version of momentum VI. And momentum decurrent, basically, instead of doing a true average of the Q value, you do a moving average of the Q value. So these two schemes are equivalent, and the moving average factor depends on the relative importance of the Kullback-Leibler divergence, lambda, and the entropy given by tau. So if lambda is much, much bigger than tau, beta will be close to 1 and will be close to a true average. And if we look at the analysis, there are two key differences between value iteration and these schemes. The first one is that you won't converge to the solution of the original MDP, but to the solution of the MDP regularized by the entropy. That's not surprising in the sense that if you had a Kullback-Leibler divergence, and if with respect to the previous policy, and if things go well, this term will vanish because you will be closer and closer to the optimal solution. But there's no way this regularization disappears. So you find it in the solution of your algorithm. And here we have a sum. So we have a square dependency of a sum of error terms. And these error terms are no longer the average of the past error, but they are the moving average of the past error. So it's almost, if you take, again, independent and zero mean samples, if you take a moving average of a sequence of such errors, it won't converge to 0. You cannot apply the law of large number, but you can say that it will reduce the variance. Roughly, if this error term here, the small epsilon, has a variance of 1, this term, which is a moving average of the previous one, will have a variance of 1 minus beta. So you can control the variance of this guy. And this G2 of K, I should have put its equation, but basically it behaves better than 1 over K, but it can be, the closer it is to, the closer beta is to 1, the slower the initial convergence of this guy would be, and the smaller the variance will be. And if beta is close to 0, this term will be equal to gamma power K, and this term will be the initial error, and you retrieve this bound. So this is quite interesting, because if you put beta equal to 0 in this algorithm, and if you put 2 equal to 0, you end up with this bound and with the classic value iteration algorithm. And if we remove the regularization in the evaluation step with entropy and Kullback-Leibler divergence, I don't know if there's an algorithm doing this, but if you want to do the analysis, you will have the same issue as with the case where you have only entropy and no regularization in the evaluation step, in the sense that you can end up with a Bellman operator that have multiple fixed points and so on and so on. So the solution for the analysis is to introduce a type 3 where you remove the Kullback-Leibler divergence. We can afford to remove this one, but you keep the entropy term to have something that converge for sure to something. And if you look at the bound, it mixes the two aspects we've seen before. So it's not a nice average of errors. It will be a moving average of the error preconditioned by a series of kernels related to policies that depends on this error. So I just won't show the bound, but it's in the paper somewhere in the appendix. And so you somehow combine the drawback of the two previous approach. So there are some limitations in this analysis. The first one is that this is okay if you have a linear parameterization and discrete actions, because you can compute the policy analytically from the Q function. So you can do you can really do things analytically, and you can consider that this greedy step is done exactly. Now the thing is that if you use deep network, you will have errors in this term. You will have an error in the greediness, because basically you will train a neural network to approximate the solution of this guy or directly to optimize the related optimization problem. And if you do so, you will have also error in computing the average of the Q values, because you will need another network to learn this H function. So you will lose the equivalence between both approach. And the last thing is that if you know deep Q network, DQN, you don't, it's abstractly approximate value iteration, but you don't really do value iteration, a full optimization between each update of the value function. So it's somewhere between Q-learning and approximate value iteration, and you cannot reasonably do a true average of Q values because it will vanish too fast. But doing a moving average is okay. So this call for empirical comparison, I will just show a few examples and discuss it very quickly. More details are in the paper. But basically, you have the mirror descent approach or dual averaging. So it's called dual averaging. It could be called FTRL. It's the equivalent scheme, which is no longer equivalent. If you take the mirror descent approach, as I said before, you can optimize directly for this loss function using a parameterized neural network, or you can compute analytically the solution pointwise and then try to get a neural network that approximates the solution pointwise. So this is what direct and indirect stands for. So you have some of three kinds of greediness, and you have type 1 and type 2. Sorry. And you have the limiting case when you consider no entropy, just the Kullback-Leibler divergence, except for the dual averaging scheme, because you cannot really do a true averaging. You need to do a moving average, so you don't have two types. And you can, here you have the temperature and beta. And there are a few questions: is are this scheme is equivalent? And you see that no, it's not the case. The result here between direct and indirect are quite close, but the result of dual averaging is a bit worse. The question is it useful to add a regularization in the evaluation step? And if you look at the difference between these two curves, the first row and the second row, the first row is but regularization in the evaluation step, and the second row is done but evaluation in the regularization step. And you see that the first row is much brighter, which means that using regularization is better. And this is even more true for high entropy. Here on the right, you have high entropy, so it's much darker here. It works less well. If you compare what happens with small entropy, the two figures are quite similar.
Yeah, quick question.
Yes.
So can we generalize from these experiments to, Cartpole is specific problem, to maybe domains? What are the limits of these experiments?
So I'm just explaining the result on Cartpole, but we have result on Lunar Lander, I guess, and three other games.
And the other question I have is that, okay, you're comparing, it's like a sensitivity analysis, I guess, what you're doing. Like, how easy would it be to find the right combination of, of coefficients if you did a grid search or something like that? Or I don't know what exactly is going on here, because, I mean, sure, like maybe the region where you have good values for dual averaging seems to be a smaller region, but if you have a procedure that somehow always puts the values there, then you would be winning at the end, right? So it's like, what are we doing here?
So the
question is how to interpret these results? Like, what's the right interpretation of these plots?
Yeah. So the thing is that many algorithms use regularization, but for example, MPO or TRPO or momentum DQN, But they often use regularization, but with other things. For example, if you take soft actor critique, which is the most well-known algorithm using entropy, they use a twin critique. And if you remove the twin critique, it changes a lot the empirical result. In MPO, you have retrace for the critique, and so on and so on. So the regularization is one of our core selling arguments. But there are other components that are important for the results we observe in the paper. So our approach here was to take the base DQN and to modify this base DQN in the simplest possible way to have the regularization. So it's just DQN, but with an additional actor. And the most simple possible implementation of what should be regularization to see just what is the effect of regularization. And the question are, does Kullback-Leibler divergence helps? Because this is what the analysis says is that you should put Kullback-Leibler divergence and you should put Kullback-Leibler divergence alone or small entropy. Our analysis says you should put regularization in the evaluation step. So and it comes for free. I mean, you just have to augment your reward with a entropic term or a Kullback-Leibler divergence term that you can compute with discrete action or with continuous action. So should we put regularization in the evaluation step? Is the entropy that useful in our experiment? And if we add some additional Kullback-Leibler divergence, does it help to add KL to the entropy? And so the plots are quite dense. And how sensitive is it also to the choice of the temperature and to beta? Because the theory says nothing about it. It says the temperature of the entropy should be small. It says that beta should be not too big but not too small, but nothing more precise. So it's ready to see. We know that the bounds are made on assumptions that are not satisfied on practice, but we want to see if we still can observe things related to this bound in the experiment. And the reply is yes.
Mm-hmm. Okay, so I don't know whether I should ask the question now or shall I ask it at the end? I don't know how many more slides there are. The quick question is whether it could be that like there's some sneaky exploitation effects happening here as well, right? So you're churning up entropy, therefore you're going to places, you get the signal, you learn faster. Altogether, maybe some middle ground when you have some entropy is going to have, for example, because of this. But it seems it could be just like, in some cases you may need this, in other cases you may not need this, and like it is a very like indirect way of controlling exploration, right?
Yeah, but here you have no entropy, for example. On the bottom, these curves are solely with Kullback-Leibler divergence. But you have a kind of explorative effect with the Kullback-Leibler divergence, because at the beginning, your Kullback-Leibler divergence is an entropy.
Yeah.
Doesn't change.
Right.
So it works well, at least for CardPol, it works well with solely the Kullback-Leibler divergence, except for the DS scheme where the entropy seems to help. So there are, I'm not pretending that the results are fully explained by the bound,
sure,
and that the bound explains the result of the converts, but that some empirical insight can be taken from the bound. And taking a Kullback-Leibler divergence helps usually, and it's a simple modification. That doing the regularization of the evaluation step, it's never worse, and it comes at free. And what kind of the scheme between not equivalent, what is the best greediness? And this depends on the problem. For some problem it's this one, some other problems it's this other one. So
okay.
If you look, for example, here you have a high entropy. So in this case, it's interesting to put the regularization. So this somehow suggests, but if you look at the case where you have no entropy, there's really the difference between both type 1 and type 2 is quite teeny. And this suggests that you should really put regularization for the entropy term, but it's not as important for the Kullback-Leibler divergence term. And if you look at what's happening here, so for a given entropy, you have from low Kullback-Leibler divergence to high Kullback-Leibler divergence. So if you put small Kullback-Leibler divergence, it will be generally less good than with high Kullback-Leibler divergence. And you can observe this for almost all value of the entropy. If you go down, it gets better. And the next slide is a similar result for Asterix, the Asterix game on Atari. And here the results are a bit more mixed, but you see that with high entropy, it usually works better. But here, dual averaging is working better than mirror descent, or at least on a larger scale. But type 1 is still a bit better than type 2 because the top figure is brighter. For direct, it's quite strange because high entropy helps a lot and high entropy destroys everything. So we cannot explain everything, but there are some empirical insights that can be taken from the analysis. And it helps a bit to understand a bit more what's happening when we put Kullback-Leibler divergence regularization inside the greediness. So this is the last slide. So I presented an unifying view of regularization in reinforcement learning with links with between many algorithms that were somehow disconnected. I don't know if someone before made a connection between, say, TRPO, DPP, Polytext, and Momentum BI. So in itself, the core things they're doing is very close or equivalent, and the way you will implement the algorithm will change things. And if you want to know more about this, so the presentation is taken from Leverage the Average, but some of the contents come from our previous paper, and you can contact me or ask me the questions right now. Thank you for your attention. And it's exactly 50 minutes.
Thank you, Matthieu. Right.
Okay, so people can leave if they want to. We're gonna stay for a little more chat. Actually, we should have some time for questions in the next 10 minutes, and even after that, we're gonna go off record and then just chat about the live and reinforcement learning. Everything.
Matthieu, apparently you said something very illegal, and the YouTube stream was removed due to a violation of the community standards. But I guess now we can continue our questions without any spying eyes, I guess. So there was a question by Aditya Modi. Maybe you can ask a question if you're here.
Yeah. So as you said, currently we don't have theoretical results on what happens when we have an approximate policy class, where you would also have errors in the greedy update step to the policy. So do you have empirical results for like a restricted policy class or like with non-linear function approximation for the value functions, where you cannot actually maintain averages, or you're not actually storing the Q functions during your value iteration updates? And if yes, how should one project the greedy updated policy back to the considered policy class?
First, I said that there are no theoretical results regarding policy iteration scheme with an average Q value. So this is not that true. I don't have such result for showing compensation of error, but if you take the Polytext algorithm, they provide a regret bound for this kind of schemes. So there are theoretical results, but not this one, and not about compensation of error. Second, empirically, it works well. For example, the momentum DQN, you have your QNet, you have your Q network with a target Q network as in DQN. So the dual averaging stuff, and you have a second neural network, the H network, that will learn the target of this network will be a moving average of the online Q network and of the target Q network. And you can learn these things. And in MD direct and MD indirect, we learn as if you just take the entropy, you can compute things analytically, even with neural networks, because it's a softmax. But if you put the Kullback level divergence, you cannot learn things analytically. So you approximate it, you project in the function space, in the policy space, using usually a Kullback level divergence. So you have your analytical solution, and you have your neural network, and you learn the neural network to minimize the divergence with respect to the solution, like it's done in Softmax or critique, for example. I'm not sure I replied to your question.
Aditya?
I got the gist of it. So, yeah,
sorry, can I have a question?
I just wanted to ask a question that was asked previously on the chat, and that was related to, and then after that, you could have your question. So the question was whether these algorithms or algorithm family is closely related to SEC-like algorithms. So it's basically, is it true that one can say that SEC-like algorithms are similar to value iteration with greedy step with respect to an average hard queue, where I don't actually know what the hard queue is, but I could guess, but my guess is as good as yours. So go ahead. So the question, is it clear?
Yeah, I think so. SAC is here. This is SAC.
Yeah.
You can really derive SAC from this scheme. So SAC is a value iteration type 1 with greediness and with all the things you need to do to work with continuous action on neural networks. But SAC is value iteration. Even if it's presented as a policy iteration scheme in the paper, it's value iteration. I mean, the algorithm. And the thing is that as you have continuous action, you say that the greedy step will be softmax according to the Q function, but the greedy step is softmax according to the Q function. You cannot even compute the normalizing factor. So you take the reverse scale to get rid of this normalizing factor, and there are a lot of tricks, and then you optimize by using a reparameterization trick in your neural network and so on and so on. But from a dynamic programming point of view, it's value iteration with entropy regularization. And the theory doesn't explain why SAC works well. That's all.
Yeah.
Sorry, can I have a question directly talking right now?
Sure.
I don't know how to put the question into the chat box.
No, go ahead.
Can we kind of like bring this idea of regularization in the dynamic programming into like more narrow down multi-color tree search setting where we don't have the analysis of the conversion, but we care about the probability conversion if we have a good policy in the same setting of regularization? Do you see that kind of connection?
Sorry, I didn't understood your question.
So this is like regularization. Can we bring this schema into like non-stationary bandit or Monte Carlo tree search setting where you don't have the full state from the root node, or you just expand through the tree and you also apply the same principle of value and policy as when you do the regularization?
So I think there are many such applications. For example, you can apply the follow the regularized leader to bandits, and this would be this kind of approach. Follow the regularized leader is equivalent to mirror descent. It amounts to using, if you work on the simplex, it amounts to using a KL divergence. And so I think many of these things already exist, but more on the online optimization iterator. The thing is that, as I said before, when working on the MDPs, the proof techniques is a bit different, and the quantity you analyze is not a regret, and so on. So there are, from the algorithmic structure, it's quite close, but you have some key difference. But I think it's more on the online learning setting that you will find application to things like bandits.
Yes. Yeah, I can see that. Thanks.
So we have some other questions that have been in the chat. Nan Jiang, do you want to start with your question? Are you here?
Yes, I'm here. Can you guys hear me?
Yeah.
Yep.
Yeah. So I'm very curious about. So at one side you showed a result that gives a linear horizon error propagation for entropy regularized a version of AVI. And as you mentioned, we know that most versions of AVI and API must have quadratic dependence on horizon in terms of error propagation. I just wonder if you have any insights or intuitions to share about how that is achieved. You know, we know that there are a few other ways to achieve linear error propagation. For example, if you output non-stationary policies, or if you happen to find a fixed point. Is the result here achieved in a similar way, or the underlying mechanism is somehow different?
So the reason for the linear dependency is that we can control, because the policies are moving somewhat slowly, and because of this averaging effect, we control the Bellman residual. And if you can bound the Bellman residual, you will propagation by the horizon. So that's the reason why.
Right.
But
okay, interesting. I'll check out the paper. Yeah.
It's in the proof.
Okay. Yeah. Thanks.
And then I think we have a question from Sriran Baswani. Would you like to ask your question?
Hello.
Hi.
Hello. Can you hear me?
Yeah.
To get the error cancellation, we had to sacrifice on the rate when there is no error. So we went from gamma to the k to 1 over k. Is it possible to have a modification that gets the best of both worlds? So you still have error cancellation, but still get the best rate when there is no error?
So I don't know. I'm not. Maybe you can improve things, but I don't think you can go back to the gamma per k because there's no free lunch. If you gain something, you pay it something elsewhere. And also,
something like variance reduction or error reduction by some other way.
So this is different. If you do a variance reduction and so on, you will play on the more on the error term. Not on the rate of convergence of the algorithm. You cannot go faster than what you would do if you were working on if you were working with the full model without approximation. But the thing also is that the 1 over k in the first iteration can be smaller than the gamma power k. And the thing also is that the true rate of convergence of value iteration, you get it not with a supremum norm, but with a span semi-norm, because you don't really care. You don't really care about the level set only of the relative values of the different actions. So maybe, but I had no clues on how to do it or how to achieve it.
Okay, thank you.
There was one more question. Tan Nguyen Tang? Tan, are you with us? Okay, I can read out the question if I find it. I've lost it. Okay. It was just like Tan wanted to have like one more summary of the takeaway of the whole regularization business, theoretical and empirical, like where are we standing?
So a big summary.
Yeah, just like one sentence take-home message, and then maybe we even close out after that.
Regularization is good. Actually, pull back about regularization and put regularization in evaluation step 2. And no, any algorithm that works
Okay, you're cutting out.
regularization and algorithm.
Okay, someone is also stopping. Yeah, that's Damian, that's you. Okay, you're muted. Okay, so start again.
So, callback label regularization is a good thing. If you put regularization, put it in the evaluation step 2, it comes for free and it doesn't harm. The effect of regularization is averaging of zeros, and many successful algorithms make use of regularization under the hood. For example, speedy Q-learning, which has very good performance bounds, comes from the, it can be derived exactly from the callback-label regularization.
Okay. Sounds good to me. All right, so I think that we should stop here. Thanks, Matthieu, again. And I'm gonna stop recording, and we can hang out a little bit more just for
some more informal chat. Yeah.
More informal chat. All right. Okay. So.
All right. Thanks everybody for joining. And,
yeah.
Well, I don't know how we violated the terms on YouTube, but.